All right, today we're talking about exponential functions. An exponential function, some key features with an exponential function is one, you're going to have an exponent, which is the reason why it's called an exponential function. So x is your variable, but it's also an exponent. Okay? So with our exponential functions, you'll notice that there's a lot of real-world applications. So a lot of the functions we're talking about are going to relate to the real world. And some examples of exponential functions would be population growth or a pandemic. But those are two examples of growth, but you can also be talking about depreciation. So like if you ever hear your parents talk about their car is worth less today than it was when they bought it brand new, that's because of depreciation, and that is an exponential function. So there's a lot of real-world applications when it comes to exponential functions. So let's look at the equation that we have here. We have f of x that's equal to bx, where b is greater than 0. And I'm going to add in another letter here, a, because even though it's not there, it is a key part of our exponential function. And so let's break down what these different parts mean. The a term is going to tell us our y-intercept, which is different from what we have ever dealt with before, because if you remember with our linear functions and with our quadratic functions, our y-intercept was always our constant. But we don't have a constant when we're dealing with exponential functions, at least not in its regular form. So now our a term is always going to be our y-intercept. Our b is our ratio. And our ratio, just like when we were talking about our geometric sequences last week, is what's telling us what's happening to that function. Is it growing or is it shrinking? And then we have our exponent here. And our exponent is what's changing. Or our exponent is what makes it the exponential function. Okay? And the reason why b has to be greater than 0, well, because anything to the 0, any 0 to a power is still going to be 0. So we always put that b is going to be greater than 0. Okay? So that means also that you will not have a negative number. So your b cannot be a negative number. It's always going to be greater than 0. So that could be a fraction or a whole number or a decimal, but it's going to be greater than 0. No negative numbers, okay? So let's look at some vocabulary words. We have asymptote. Asymptote, and I'm going to do this in blue. Okay, our asymptote is just a line, and it's an imaginary line. That a graphed function approaches but never touches or never crosses. It will never, ever, 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 ever cross. See that word never? It will never, ever, ever, ever touch or cross that asymptote. Then we're looking at what an exponential growth function is. Okay? Growth is an exponential function where b is greater than 1. An example of this would be y is equal to 4 to the x power. Now, in this case, our a term would just be 1 because if there's not a term there, if there's not a parentheses, then that means our a term is 1. Then you would have 4, which is your ratio, and then you have x, which is your exponent. Okay, as long as this b term is greater than 1, you have an exponential growth function, meaning it's getting larger and larger. The other type of function that you can have is exponential decay. An exponential decay function is an exponential function where b is between 0 and 1. So an example here would be y is equal to, and we're still going to put that 1 there for our a term, but we could have a fraction here of 1/2, 3/4, anything less than 1 to a power. So again, my a term would just be 1. My ratio is 1/2, and this ratio is between 0 and 1, and then we have our exponent. So let's take a look at the differences between these two functions. So first we're going to look at growth. Okay? When we're looking at our functions, we're always going to read from left to right. Okay, so if we're going from left to right, what's happening? Well, what's happening is our x is increasing, and as x is increasing, y is also increasing. So that's why it's an exponential growth function, because, and we can fill this in down at the bottom now, it rises from left to right, and then it's going to ask about what our asymptote is. Well, our asymptote, again, is that imaginary line that function is never, ever, ever going to cross. And our asymptote in this equation is going to be y is equal to 0, because it's always going to be a horizontal line. And all of our horizontal lines are always going to be written in the form of y equals. Our domain for this function, just like it was for quadratics, is always going to be all real numbers when we're talking about exponential functions. And that's because this exponential function could have any value on that x-axis. Our range, I'm going to do this in the other blue, our range is going to be any possible y values. Well, I can't have a y value below the x-axis, so my range here is going to be greater than 0. And it does not include 0 because, remember, it never crosses or touches that asymptote. So it would not be equal to, it's just y is greater than 0. And then we have our y-intercept. And our y-intercept is going to be 1. And you can tell that because, and I'm going to scroll back up, when we're looking at this function, we should really think of this as f of x is equal to 1 times 2 to the x power. And that 1 is always going to be our y-intercept because that 2 is our ratio. And I put 2 and it shouldn't be, that should be x power because that's the variable, that's what's changing is our input. Okay. So our y-intercept here is going to be 1. Now let's look over at our exponential decay. So here, again, I'm going to rewrite this as f of x is equal to 1, because that's going to be our y-intercept, multiplied by our ratio to the x power. Okay, our ratio is the 1/2, and then we have our variable. And this is showing decay because our ratio is between 0 and 1. And again, I'm still reading from left to right. So what's happening as my x increases, what's happening to my y? My y is decreasing. And that's why it's called exponential decay, because it's getting smaller and smaller and smaller. So it falls from left to right. Our asymptote, the line that it never crosses, is still going to be y equals 0. Our domain is the same because we could have any possible x value for our input. There is no limitations on our domain, so it's going to be all real numbers. And our range here is still going to be y is greater than 0. Because look at, your range didn't change from growth to decay. Your range is exactly the same, and that's because that function is still going to be above the x-axis. So you could have any possible y value, but it can't be 0 or below. So y is going to be greater than 0. And our y-intercept here, where does that cross the y-axis? Well, it's at 0, 1. Oops. Don't want to write in highlighter. 0, 1. And that's just this point. And that's because that's our a term. Okay, now let's go ahead and look at some examples. It says use the graph to identify the characteristics listed below. Okay, so I'm going to rewrite this function so that I know what my a is. I'm going to have f of x is equal to 1 times 1/4 to the x power. And again, this 1 is telling me my y-intercept. And you can see here that my y-intercept is 1. So I can go ahead and fill that in right away. My ratio is 1/4. And if my ratio is 1/4, that means that I'm going to have exponential decay. And I can also visually see that because as my x is increasing, my y is decreasing. My asymptote, which is hard to tell in this picture, but that line should not be touching that x-axis. So my asymptote is going to be y is equal to 0. My domain here is the same. It's all real numbers. And my range is going to be anything greater than 0. All right, so that was number 1. Now let's look at our next example. It says use the graph to identify the characteristics listed below. Is this growth or decay? Well, first, let's rewrite this in a form that makes sense to us. So we're going to have f of x is equal to, our a term should be 3 here. Because that's our y-intercept. 1, 2, 3, 4. Sorry, our a term should be 4 here. So what's happened? They gave it to us in a different format. We'll talk about that in just a second. So we're looking at this function, and we can see that it's growing from left to right. As my x is increasing, my y is increasing, so I'm going to have exponential growth. My asymptote here is changed now because that line is getting closer and closer to this point, which is y is equal to 3. So that will now be my asymptote. Y is equal to 3. Our domain here, that has not changed because it's still all real numbers, because anything along this x-axis could be our input. And then our range is y has to be greater than 3. And look at how our range relates to our asymptote. And then we have our y-intercept. Well, they gave us the graph, so it's easy for us to identify our y-intercept, which is right here, which is 0, 4. But why is that our y-intercept? We'll have to get back into that later, but the reason why that's our y-intercept is because of this right here, which is our k term, which we're going to learn about in one of our next videos. So if our asymptote is greater than 0, that's going to change our y-intercept. All right, one more example to get through today. It says use the xy table to graph the exponential function, then answer the questions below. So we have f of x is equal to 2 to the x minus 1. Is this growth or decay? Well, just like we did before with our tables, we're going to have to do that again with our exponential functions. So we're going to plug in this x value to find our y value, to find our output. So the first thing we're going to do is find f of 0. So f of 0 is going to be equal to 2 to the 0 minus 1 power, which is equal to 2 to the negative first power, which if you remember from our exponent rules at the beginning of the year, if we have a negative exponent, what happens is it becomes a fraction. So we have to put it under 1. So it's 1 over 2 to the first power, which is just 1/2. So that means when my x is 0, my y is 1/2. So it would be right, actually it would be a little bit lower because that is 2. So I'm going to be right here. So that means that my y-intercept is going to be equal to 0 and 1/2. What is the range of this function? Oh, sorry, we need to finish doing our inputs. So we have f of 1. So now we're going to have 2 to the power of 1 minus 1, which is going to be 2 to the 0 power, which again, if you remember your exponent rules, anything to the 0 power is going to be 1. So when we have f of 1, or our input of 1, our output is also 1. So we can put our point. Then we're going to do f of 2. So that's going to be equal to 2 to the 2 minus 1 power, which is equal to 2 to the first power, which is just equal to 2. So when my input is 2, my output is 2. I'm going to do f of 3. So I'm going to do 2 to the 3 minus 1 power, which is equal to 2. Well, 3 minus 1 is 2, so 2 squared, which is equal to 4. So when I input of 3, my output is 4. I'm going to find f of 4. So 2 to the 4 minus 1 power, which is equal to 2 to the 3rd power. So all I have to do now is multiply that 4 times 2 again, and I'm going to get 8. So when my input is 4, my output is 8. And I need to do f of 5 as well, so I'm going to do that along top up here. F of 5 is equal to 2. Oops, I knew that was going to happen. To the 5 minus 1 power, which is equal to 2 to the 4th power, which is just equal to 16. So when my input is 5, my output is 16. All right, that's our pages, our 2 pages of notes for Monday, April 5th or Tuesday, April 6th, depending on when you're taking your FSA writes. We'll work on the practice problems in the next video. Bye.